Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, musical instruments. Musical instruments come in all shapes and sizes and forms, but from a physicist's point of view, most of them have a lot in common. They essentially all involve some extended medium like a string or a column of air or the surface of a drum that vibrates back and forth, which is another word for oscillates back and forth, with many of the characteristics of a harmonic oscillator. Well, before I start talking about specific musical instrument categories, I won't, I got a violin here and a recorder, but they're examples of sort of their classes of instruments. This is a stringed instrument, this is a wind instrument. Before I look at this particular individual ones, a few definitions or words about just music in general. First off, a harmonic oscillator, which is going to be deep into all this whole story, a harmonic oscillator has a period of motion that is independent of the amplitude of that motion. Well, in the world of musical instruments, instead of talking about the period of motion, that is the time from the start of one cycle through that cycle to the end of the cycle, we'll talk about frequency of oscillation. And what a frequency is the number of full cycles that a harmonic oscillator or any oscillator goes through per second or per unit of time. So it's the reciprocal of period. So period is how many seconds it takes to go through one cycle. Frequency is how many cycles you go through per second. Frequency is 1 over period, period is 1 over frequency. Simple as that. So as the period gets shorter and shorter, the frequency gets larger and larger. Okay, another thing to talk about is that in the language of music, we don't talk about frequency, literally frequency. That's physicists and engineers' language. We talk about pitches, but it's the same thing. So the pitch of a tone in music, really, you look under the hood, that's really talking about frequency of the sound associated with it. I'll talk toward the end of this video about sound itself, but sound is all about rhythmic motions that we'll create with musical instruments, and ultimately we hear them having traveled typically through the air. Okay, so with that introduction to the language, how about the instruments? Well, a violin is an example of a stringed instrument, and what it has at its heart is a string. There are four, let's consider one string. And that one string can vibrate. It has an equilibrium, and it's a stable equilibrium, and it can vibrate about that equilibrium. Again, vibration and oscillation, they're just different words for essentially the same thing. The context may matter, but we don't worry about it. So a string, it has a stable equilibrium. If you pull it taut, I should say a string just plopped on the table. Do I have a string kicking around here? Yeah, let's look. So here's a nice thick string you can see. And if I just plop it on the table, nothing interesting. It has a shape, but it's indifferent to small variations in that shape. Who cares? All right? But once I put tension into it, I pull on the ends in opposite directions, so it has this forces within the string that act to bring it to a straight line shape. Now it's got an equilibrium shape, a straight line. And if you bend it away from that shape, you have to do work to do that. It takes energy to get it away from its equilibrium shape, and it develops restoring influences. And the restoring influences push it back towards center, back towards its equilibrium. It's a stable equilibrium, and so far we're heading towards harmonic oscillator land, but it's kind of a complicated object because it's got many different parts to it. We can sort of divide it up into little segments from left to right and think, they can all move around, and how does this thing behave? Well, when the dust settles in sort of the analysis of how a string behaves when it's under tension, it turns out that you can simplify how the string behaves into a series of what are known as vibrational modes with an M. And the vibrational modes are sort of the most basic structures that the string can have that have simple dynamic behavior, that they move through their motion in a very simple, easily characterized way. And the most simple of the vibrational modes that a string can have is its fundamental vibrational mode, and that's a single arc, and it actually follows the trigonometric sine function. I can't show you that sine arc here. It looks about like this, and it bounces up and down like that. And I will leave it to other contexts to actually show you this vibration in real time. But that vibration back and forth, very much like the vibration of a jump rope up and down, it's got enormous amount in common with the jump rope. That motion is the fundamental vibrational mode of the string, and it's the primary thing that's going on when I pluck one of these strings. So I'll pluck one of these strings to get it going. That most of what's creating that particular sound originates in the rhythmic motion of the string up and down in that fundamental vibrational mode. In that fundamental vibrational mode, when the string is moving like that, if you were to sort of stop at any given moment and analyze the situation, you discover that whenever the string is not straight at its equilibrium, whenever it's displaced from that equilibrium, it's experiencing restoring influences, pushing it back towards equilibrium. And the strength of those restoring influences is almost exactly proportional to how far it is from equilibrium, to its displacement. So when the string is vibrating in its fundamental vibrational mode, it is meeting the requirements of a harmonic oscillator. It has a restoring influence that is proportional to its displacement from equilibrium. So in concept, it is a harmonic oscillator. It's a weird looking one, it's extended, but it's a harmonic oscillator nonetheless. And the string actually could behave not just as that harmonic oscillator. So that's a harmonic oscillator, weird shaped, extended, but it's a harmonic oscillator. It can also act as two harmonic oscillators, like this. This is another of its possible harmonic oscillator modes. This is another vibrational mode that it again behaves as a harmonic oscillator. Two half strings. Right now, if I put tension into this, of course, it will pull straight. So I'm illustrating this by playing. Okay, but the string can vibrate as two half strings with one arc up and one arc down, and then moments later the reverse back and forth, and the middle stays put. That's what's known as the second harmonic mode of the string. Incidentally, as we look at this, these structures, it's the fundamental mode, what's called the second harmonic mode. There is a third harmonic mode where it's vibrating as three 1/3 strings, 4 1/4 strings, and so on. Each of those more complicated modes has some structure in it that we can pay attention to. Even the fundamental mode, this mode, has some structure. At the ends of the string, on one of these typical stringed instruments, the ends don't move. They stay motionless. And we give them a name, those motionless parts, that we call them nodes with an N. So there's a node on the right and left end of this string when it's in its fundamental vibrational mode. The middle, where it's going up and down the most, up and down, that's called the antinode, the place of maximum motion during the vibration. So the fundamental vibrational mode is characterized by two nodes, one at the end and one at the other end, and one antinode in the middle. When the string is vibrating in its second harmonic mode, which I'm having trouble illustrating here at the moment, there's about it, right? It has two antinodes, the two maximum excursions away from equilibrium, and one extra node in the middle, a spot that doesn't move. So if I did this properly, I actually had the string vibrating, that node spot would sit still as the whole thing sort of worked its way around that node. So strings, first when you pull them taut, they are suddenly able to vibrate as a collection of harmonic oscillators. The simplest of that collection is the fundamental mode, which is a single arc and has one antinode in the middle and two nodes at the ends. The next most complicated mode of vibration, and therefore harmonic oscillator that string can vibrate as, has two antinodes, one at each, the two half strings, so one's going up, one's going down at any given moment. So those are the two antinodes, and there are three nodes, one in the middle now, and then two at the ends, and so on. This whole dancing motion that the string makes is that when it's vibrating in that mode. You know, I get it. There. It's now actually vibrating, and that's the fundamental mode. And I'm going around in a circle in order to do this, like a jump rope. But the physics is actually the same as if it went straight up and down. It doesn't matter. That motion, up and around that, it looks like a wave. And technically, or according to a physicist, it is a wave. It's a wave that doesn't go anywhere, left or right. And so it's dancing in place. And such waves are called by physicists standing waves. So this is a standing wave, and standing waves are common. They routinely occur in systems that are complicated enough to have an extent. So this has an extent. That is, it's not a single object. It's not a ball. It's not a mass on a spring, which are just one thing. It's got no dimensions to it, really. This thing's got dimensions to it. It goes from left to right. It's a good chunk of a meter. So it's an extended object. And extended objects have the ability to exhibit standing waves. Their motions can be characterized by standing waves, these dancing in place waves. The simplest of which is the fundamental vibrational mode of the object. The next one is, and I'm sure I can't get it, the second harmonic, in this case, the second harmonic motion of the wave. They're just different vibrational modes, where the mode has been identified as a simple way in which the system can move that's easily characterized. And in this case, each of these modes dances differently. They also dance at different frequencies. That is, there are different numbers of cycles per second that go with them. And correspondingly in music, different pitches. So a string that is pulled taut can vibrate as one single string, the fundamental mode, with its own pitch. And the pitch, we'll see, is determined by various things. We don't get to choose it given those things. It comes naturally. It's the natural rhythm of the harmonic oscillator that is this fundamental mode. When it's vibrating as two half strings, it's got a different pitch. And interestingly enough, that pitch and the frequency behind it, the frequency is the physicist's word for it, the frequency is twice as large as the frequency of the fundamental mode. So the pitch is increased, and in the world of music, it's increased by 1 octave. An octave in music is a factor of 2 in frequency of the pitch. So a string, so how to summarize this? A string that is pulled taut has an equilibrium shape, a straight line. And it can vibrate about that straight line. And if you go looking at the vibration and you try to distill it down to its most basic, essential character, pieces of the vibration, not of the string, but of the vibration, you'll realize it's best to characterize it in terms of vibrating in the fundamental mode as a single string. Is it vibrating in the second harmonic mode as 2 half strings, vibrating in the third harmonic mode as 3 1/3 strings, and so on. Each of those modes has its own frequency, and they differ by factors of the number of antinodes. The fundamental goes at frequency 1, let's say. The second harmonic goes at frequency 2, twice the frequency of the fundamental. The frequency of the 3 1/3 strings mode goes as 3 times the frequency of the fundamental. The fourth quarter strings vibrates at 4 times the frequency of the fundamental. They're going up at integer multiples of the fundamental, and that's why they're called harmonics. Second harmonic is twice the frequency of the fundamental. Third harmonic, 3 times the frequency of the fundamental, and so on. There are other extended objects that have vibrational modes that don't have this lovely integer multiple relationship between their pitches and their underlying their frequencies. The head of a drum has different vibrational modes, but they are not integer multiples. Their pitches slash frequencies are not integer multiples of the fundamental mode's pitch frequency. Okay, so let's go back to strings. I gotta finish the story of strings here properly. So what determines the frequency slash pitch of a string's fundamental mode? Where do we get started? Well, like any harmonic oscillator, it's a weird looking harmonic oscillator, but it is one nonetheless. Like any harmonic oscillator, it goes through its motion, and there's a battle between a restoring force that keeps trying to push the string or the object towards its equilibrium, and an inertial aspect that tries to keep doing what it was doing. So those two fight each other. The inertia wants to keep going. The restoring force says, come back through equilibrium. Okay, the inertial thing comes back through equilibrium, overshoots. And then now the restoring force says, come back. The inertial thing turns around, comes back through equilibrium, and overshoots, back and forth. So the frequency and corresponding to the pitch depend on this battle between restoring force and frequency and inertia. Well, the more inertia there is, the slower the battle is going to be, because the turning around process becomes slower. So if you increase the mass in the string, you will lower the frequency and take the pitch down, lower pitch. So mass matters. So we can think of that just as mass of the string. More massive strings are slower and vibrate at lower frequencies and lower pitches, all else being equal. So that's one observation. Second observation is the tension in the string matters. The tighter the string is pulled, the stronger the restoring forces become, and the faster the motions become. Now the restoring force drives things through their motions faster, and you get a higher frequency, higher pitch. So tension favors higher pitch. The last thing is the length of the string matters. The longer the string, the weaker the restoring forces become. Because if the string is quite long, pulling the middle 1 centimeter away from center becomes a trivial deformation of the string. It's barely bent at all. So for a long string, the restoring forces are pretty weak. You can go off center easily. If the string's very short, pulling it a centimeter off center, away from equilibrium, is a huge deformation of that string, and it hates it. So it pulls back fiercely. So short strings have stiffer restoring forces, and they go through their motions faster. In fact, shorter strings have sort of two reasons why they go extra fast. They have less mass because the string is shorter. There's not as much, you eliminate the mass out in the wings. And they also have a stiffer restoring force. So those both favor faster motion and a higher frequency, higher pitch. So if you go to stringed instruments, most stringed instruments, and I will assume virtually all of them, they will have strings of different masses. And this is a thick string here, a thin string. The thin string is going to go through its motions faster, so it's got a higher pitch than the fat string. So all else being equal, the fat string just goes slower. More mass, more inertia. Second thing to observe is as you change the tension, more tension, you get a higher pitch. So this let me take the low string here. I haven't tuned this for anything. It's the world's cheapest violin. So there's with the string pretty loose. Let me tighten the string a little. It slips, of course. I'm going to try to tighten the string. So the tighter the string is, the stronger the restoring force becomes, the stiffer the string, and the faster it goes through its harmonic oscillator motions. The last thing to pay attention to is the length of the string. If I shorten the string, which I can do not by actually changing the violin, but simply by sort of pinching off the end of the string, if I take the string, the full string on this high-pitched string is, it's about, it's a certain pitch. If I shorten it, I get higher pitches. And that's because I am both reducing the amount of mass in the oscillating system, and I'm stiffening the restoring force on that mass, so it goes through its motion faster. So the bottom line is stringed instruments have a lot of ability, a lot of range of pitches they can produce, where the controlling the pitch is done by choosing the mass of the string. More mass makes things go slower, lower pitches. By controlling the tension in the string, more tension stiffens the restoring force and increases the pitches and frequency. And lastly, the length of the string. The shorter the string, the stiffer the restoring force and the lower the mass, the faster it goes through its motion. The higher the pitch, the higher the frequency. All right, that's a pretty good coverage of stringed instruments. What about wind instruments? Well, wind instruments, the thing that vibrates in them is the wind, basically, the air. It's not the instrument itself, not the physical instrument. So this one's made of, it's plastic. If it were made of metal, of gold, I don't know, whatever, makes no significant difference. It's not the material, this substance that's vibrating, it's the air column inside. That's the extended object that has its vibrational modes. And the vibrational modes of these wind instruments, what's sort of vibrating? The air in this room has a uniform pressure and density, density and pressure. If it didn't, air would accelerate from the high pressure toward the low pressure, and we pretty soon would wash away any overall differences in pressure. But once you confine the air inside a pipe, you can allow that air now is protected from the outside, and its pressure, and I'll leave aside density, but its pressure can make excursions up and down about atmospheric pressure without much trouble. They won't stay above or below. Things will move if they're above and below, but they can temporarily get above or below atmospheric pressure, and that allows for vibrations. And if you just consider a pipe that goes from left to right, here's a little pipe. It's nice to have some of everything randomly sitting around in my room. So here's a little pipe. It's open actually at both ends. Hi, I can see you. Okay, it is possible for us to temporarily make the air pressure in the middle above atmosphere. How do we do that? We pack the air molecules too tightly in that middle, so the density is too high. And having done that for a moment, we have high pressure and density in the middle of the pipe. Well, what's going to happen when we let time start happening? What's going to happen is there's atmospheric pressure out here, high pressure inside here, above atmospheric. There's going to be some acceleration. The air is going to push and begin to flow out of the pipe at both ends. It's going to go rushing left and right simultaneously up the ends. And it will very soon get rid of the high pressure in the middle. The air will flow out to the point where this is back to atmospheric pressure in the middle. But at that point, the air at the ends of the pipe is moving. It's got inertia. And it will overshoot its equilibrium. The equilibrium is uniform pressure and density across the entire pipe. It will have started with the middle above equilibrium, displaced from equilibrium, and whoosh, the air will rush out until it's at equilibrium, but moving. And inertia will carry it beyond equilibrium. It will overshoot its equilibrium. It's a weird situation. The air is rushing out of both ends, and it will overflow away from it'll flow too much away from the center of the pipe. The pressure and density inside the middle of the pipe will drop below atmospheric pressure. It'll be a partial vacuum in there. We'll be away from equilibrium again. And now the air will turn around, accelerate backwards, and flow back in and go above atmospheric again. So there will be a vibration. And this vibration is the air pressure in the middle of the pipe making excursions above atmospheric pressure, through atmospheric pressure, overshooting to below atmospheric pressure, coming back, overshooting, back and forth, up and down. And as that's happening, air will rush in and out of the ends of the pipe over and over again. That is the fundamental vibrational mode of air in a pipe that's open at both ends. It's another extended object that has vibrational modes. And that vibrational mode is another harmonic oscillator. Again, it's weird looking. It's not a single object on a single restoring force system. It's a complicated object, but it has all the characteristics of a harmonic oscillator. It has a stable equilibrium, namely uniform pressure and density across the entire pipe. And when you displace it from that equilibrium, it experiences restoring forces that push it back, restoring influences that push it back. And those restoring influences are proportional to how far it is away from equilibrium. That is, the more the pressure and density build up in the middle, the stronger the influences are trying to get it back to equilibrium. And the proportionality is there. So it's a harmonic oscillator. It has a period of motion, or equivalently, a frequency of motion, or equivalently, a pitch that doesn't depend on the amplitude of motion. And I neglected to say that in the context of stringed instruments, but let me come back to that. Whenever you have one of these vibrational modes that fulfills the requirement of a harmonic oscillator, it has a restoring influence that's proportional to displacement from equilibrium. You have all the features of a harmonic oscillator, particularly a frequency or period or pitch. These are all directly related quantities that doesn't depend on the amplitude of the motion. In a stringed instrument, what that means is that the pitch produced by one of these strings doesn't depend on how far the string moves, and therefore on the volume of sound. Not the word volume, the loudness. The word volume I use by accident. If I use by accident, volume in physics is like a liter, like it's a quantity of space. So I shouldn't use the word volume in talking about musical instruments. I do it carelessly, so if I do, I apologize. But the real issue here is the loudness, whether the string is playing softly or loudly. Therefore, low amplitude of motion, large amplitude of motion, same pitch, because it's a harmonic oscillator. The same is true for a wind instrument. Whether you're playing the wind instrument softly or loudly, small amplitude, large amplitude, you get the same pitch. It's a harmonic oscillator. Okay, well, I told you that the strings can vibrate in more than one vibrational mode. What I didn't tell you also is that they can vibrate in more than one vibrational mode simultaneously. And those two different modes don't bother each other. So it can vibrate in its fundamental mode while it's vibrating in its second harmonic mode. They have two different pitches, but that's okay. So the string produces two different sounds simultaneously. And that mixture of the fundamental and its harmonics gives character to the sound of musical instruments and often allows us to distinguish one from the other. Different musical instruments have different mixtures of the fundamental and the various harmonic modes. Wind instruments, same situation. The fundamental mode I've told you for the pipe, open pipe, that is open at both ends. Some musical instruments are open at one end and closed at the other, and that changes the character. When it's open at both ends, it can have one fundamental mode which has one antinode in the middle. The antinode, this is a pressure antinode, where the pressure makes maximum excursion up above atmospheric pressure and maximum excursion down below atmospheric pressure. That's the antinode, up and down, up and down. It can also vibrate can it vibrate in second harmonic mode? That would be, it can vibrate as, I don't think it has a second harmonic mode. I think the second harmonic mode would be the air flowing here, this being a maximum pressure. No, I don't think it has a second that may be wrong. I think it does have a second harmonic mode. Plan ahead. Where air is rushing in one end, piling up here, rushing out the other end, and making a partial vacuum over here, and in between there is a slope from high pressure to low pressure. I think you can have that. And that would be at twice the frequency of the fundamental. So the air, basically you can have these more complicated structures of air pressures and air densities in the middle of the pipe. So you get these harmonic modes as well. And they can be present simultaneously, so you get complicated sounds. All right. last thing to do, and before I come back to how you actually get the sound, produce the sound, and what is the sound, is to look at drum heads. These two musical instruments classes all involve things that have essentially, they're extended objects, a string, a column of air, that extends in one dimension, one direction, left to right. The head of a drum is an extended object, but it extends left to right and forward and backward. It's a surface. It's more complicated. And it has a fundamental vibrational mode, the whole thing moving down, the whole thing moving up, and it's a harmonic oscillator, you know, everything works out, yay! Except life gets a little more complicated for the other vibrational modes. You can't just sort of like slice it in half and have one half drum and the other half drum. They don't look the same anymore because if the drum is a round, a cylindrical top, it's now you've got two half moons going up and down as the second vibrational mode of some sort. The upshot of this is that the pitches that you get in these more complicated vibrational modes, which are there, the pitches are not integer multiples of the pitch of the fundamental, or the frequency of the fundamental. And so calling them harmonics becomes not right. Harmonics are really associated with integer multiples of the fundamental pitch. So they're called something else. They're called more generally overtones. So stringed instruments and wind instruments generally have harmonic overtones. They're harmonics, or just harmonics to be short. Drums, they're not harmonic overtones. They're just generic overtones. Something more, they're higher pitches, but the frequencies are not very easily related to the fundamental frequency / pitch. Okay, so that's about drums. And now let's come back to how do you get the whole thing going? Well, in a drum, it's pretty easy. You whack the surface with a stick, and you do work on the surface. You push it away from equilibrium, and then it vibrates back and forth about equilibrium until it's gotten rid of the extra energy you put into it, and therefore can settle at equilibrium. So drums typically end up as a thump as they start, big, they go from loud to less and less loud till nothing. And that same sort of thing can happen with a string if you pluck it. If you take the string and you pull it away in a single event, pull it away from equilibrium and let go. And again, the world's cheapest violin doesn't work very well, but the idea is okay. You pull away from equilibrium and then you let it vibrate and it gets less and less and less and less. So it goes immediately to maximum loudness, and then it works its way to softer and softer. And we know from hearing that, that's being plucked. That violin or that guitar or that other stringed instrument is being plucked. We hear it goes loud and then decay. But another way to get it moving, I should show you with a wind instrument. You can probably get this guy going too. If I just you can hear that vibration. That's probably the fundamental vibration of this guy. Again, by plucking it. So the drum you can pluck it with a hammer, with a string you pluck with your finger, with a pipe you can pluck it with your finger, and so on. The other way to create the music is to rhythmically push on the extended object, push it away from equilibrium a little bit with each cycle. So every time when you take the string, when it's pulled taut, find the middle, or somewhere in the middle, push it rhythmically as it vibrates. So every time it's up here, you push it down. Every time it's up here, you push it down. Every time it's up here, push it down. And do work on it every cycle. And that's what bows do. So I don't have a bow, but a bow pulling across the string grabs the string as it's coming towards, as it's being moved with the bow. It grabs onto the string, pulls the string a little distance, does work on it, and then releases the string. And then it lets the string go through half its vibration, come back, grabs it again, gives it a little work on it. A little work each cycle. And it gets going more and more and more and more. And that, we can hear that with violin, with a bowed violin or something equivalent to a bowed violin. You hear the sound start soft and build up more loudness as the bow puts in more and more energy and sustains the vibration going. The same is true of a wind instrument, and a recorder is actually a good example of this. we don't normally pluck wind instruments, get them going pop and let them decay. Instead, we rhythmically add energy with each cycle, and one of the classic ways to add energy each cycle is with a whistle, or anything like whistle. What a whistle is doing is it's allowing you to blow air across the end of the pipe in a way that rhythmically pushes on the air column. Whenever the air column is moving out of the pipe, the air from your blowing joins that air leaving the pipe. Whenever the air is entering the pipe, the air from your mouth joins the air entering the pipe and adds to it. So that rhythmic push, help the air out, help the air in, help the air up, help the air in, gets the air bouncing back and forth more vigorously, so you can get the volume of the loudness of the instrument to build up. It starts soft and gets louder. I probably can do that here, even though I don't have a whistle. Blowing across the opening of a pipe will do the same effect of pushing, joining the air going out, joining the air going in. That's the same tone. It's hard to hear it. Boom, boom. I don't want to imitate it. I'll stop. That's the pluck sound. This is the bowed sound by blowing across the top and bottom. Obviously, I'm not a flautist. All right. Last part of the story, sound. So where does the sound come from? Well, for a wind instrument, the sound is really the air going in and out of the ends of the pipe. And things are different if one end of the pipe is covered, but I won't worry about that. That's in the book. The air going in and out joins the air in the room to a good extent, in and out, and it launches waves through the air in the room. Sound in air is a wave that travels through the air. And the waves up until now, I told you that the string bouncing up and down in place, that's a standing wave, and standing waves are common in extended objects that are limited, they have an end. So this string ends at my two hands, and so it's an extended object that is limited, and the vibrational modes of an extended object that is limited are standing waves. The same is true in a pipe. The extended object is the air, and it is limited by the ends of the pipes, and its vibrational modes are standing waves in and around the pipe. Same with a drum head. Not surprisingly, it ends at the ends of the drum head. With an extended object that doesn't end, like the open air, it has vibrational modes again, and they are vibrational modes that don't stand; they travel. So they're traveling waves. Mathematically, you can describe traveling waves in terms of standing waves and standing waves in terms of traveling waves, but it's too complicated. Let's just leave it as that distinction. If the extended object ends, worry about it in terms of standing waves. If the extended object never ends, worry about it in terms of traveling waves. And the traveling waves that go through air are very much like the waves that live inside a pipe, except they're not divided up into specific modes, fundamental, second harmonic, third harmonic. They're any old possibility. Air supports any possible vibration at any possible pitch. And otherwise, they're similar, except that, of course, they travel. I should point out that on a string, the standing waves involve an excursion, something moving at right angles to the wave's sort of end-to-end character. This wave extends from left to right. That's the character I'm talking about. This is a left-right wave. But the motion that underlies that wave is an up and down or left or toward you and away from you motion. And so this is described as a transverse wave, just to give it a name. The wave is along this direction. The motion underlying it is at right angles to that direction. It's transverse. For sound, for air columns, that's different. The wave extends from left to right still when I'm getting this guy going. But the motion underlying that wave is also left-right, in the same direction as the wave. That's called a longitudinal wave, just to give it a name. Why I say this is because air carries longitudinal traveling waves. When I'm talking here, and the sound is traveling off in various directions, it's traveling as the air bunching up and unbunching, compressing and rarefying back and forth as it does inside the pipe, except those rarefications and expansions, they travel. They scootle along. They behave like harmonic oscillators too. The whole thing's all there. And they whiz along through the air, and they travel at a particular speed, which is about 330 meters per second, or about 1,000 feet per second in ordinary conditions. So I clap my hand here, whoosh, I send off these longitudinal waves, whoosh, off they go, and if somebody's 1,000 feet away, it'll take them 1 second before they hear my clap. All right, so the instruments have to launch those traveling waves and through the air. A wind instrument does it pretty naturally. The air column that's vibrating in and out of here is not super efficient at launching these traveling waves. You can make it more efficient by putting a bell at the end of an expanding shape at the end of the column. And that's why some fair fraction of wind instruments, they may be called brass instruments, but they're still wind instruments, have a bell-shaped end. It helps convey energy from the column of air vibrating inside the instrument to the air out in the outside world traveling off as sound. So this is pretty natural, the connection. A string has more trouble trying to launch sound waves. The string vibrating back and forth has to figure out a way, basically, to convey some of the energy associated with its vibration. This is the excess energy you put in either by plucking it or by bowing it. It has to convey that energy into the air, get the air vibrating, get the air to go above normal pressure density, below normal pressure density, and so on. Strings are not good at doing that. So a string vibrating back and forth, this string goes back and forth, I'll go up and down, up and down. The air pretty much ignores it. I mean, apart from various drag forces, the air, if the string goes up, I'll lift and lower the string. As the air goes up and down, as the string goes up and down, the air just scoots around it. So this string right now is doing a terrible job of compressing or rarefying the air. The air just flows around it. It's not managing to squish the air tightly and unsquish it, which is what's necessary to launch sound. My hands clapping launches sound nicely because I shove the air together up to high pressure and density, and then I let it out. And that creates these excursions above and below normal pressure and density that travel as waves, as traveling waves, and our sound, we hear them. The string isn't like my clapping hands. It's like the sound of one hand clapping, never thought of that, but I did just now. No sound, right? Because the air just goes, oh yeah, you're moving your hand, I will just flow around you to the back. And vice versa. So terrible at launching sound. To launch sound, apart from using air itself as the vibrating medium, to launch sound with a string, you need help. You need a surface. Surfaces are a lot better at launching sound than strings. Strings are too skinny. The air just goes right around them. Surface, if the surface is big enough, doesn't give the air such an opportunity to get around to the back. So if you have a big surface and you shove on the air, you squeeze it, you compress it, increase its density and pressure. So stringed instruments, maybe universally or pretty nearly universally, have some surface associated with the string. It's not just the string, the surface matters. And in a violin or a guitar, of course, it does have a surface. The string's vibration conveys some energy to the surface, and the mechanism for that is idiosyncratic to each instrument. It's complicated, but the violin has a connection between the string and the surfaces of the violin. So the vibrating string causes the surface to vibrate with it. The surface doesn't have any. It's not behaving as a harmonic oscillator. It's just there to move with the strings. Whenever the string is going one way, the surface tries to move some corresponding direction, and then they both reverse together. And the surface then moving back and forth does manage to compress the air and uncompress it, or rarefy it back and forth and launch sound waves. So a violin with no body would be almost silent. You need the surface. Same with a guitar. And an example of that is like acoustic guitars have surfaces that move nicely with the strings and therefore launch sound nicely. Electric guitars, by and large, have surfaces that just don't move much and they don't launch sound well at all. As a result, electric guitars are almost silent if you're playing them without any electronics. They use an electronic system to pick up the motion of the string and produce sound separately. For a long time, there's almost no sound coming from the instrument itself. It's traveling out of the instrument as electrical stuff, which has no sound associated with it immediately. It goes through amplifiers and stuff, and then it goes to a speaker, and the speaker's job is to create the sound for the first time. And so electric guitars create sound in quite a different way than an acoustic guitar. All right. With that, then, I think I've covered everything I wanted to cover in the context of musical instruments. They are generally built around extended medium with media with limited ends, with limits, so that they have standing waves as their vibrational modes. Each vibrational mode has its own pitch. In most one-dimensional instruments like strings or columns of air, the vibrational modes have pitches that are integer multiples of the fundamental pitch, and so they are harmonics. And actually, harmonics sound particularly good to our ears, or comfortable or familiar to our ears, and so we hear these stringed instruments as very melodic. Surfaces like drum heads, they do not. Their overtones are more general. They are not harmonics. They're not integer multiples of the fundamental, and they sound less musical to us in general. All of these are, for the most part, harmonic oscillator systems. That is, the modes behave as harmonic oscillators. There are exceptions. There are some instruments in which the amplitude of motion affects the restoring forces, and therefore they have the pitch / frequency does depend on the loudness, and those instruments sound twangy. And actually, my cheapo violin here has some twang to it. So instruments where when you pluck them, they go pew down in pitch or pew up in pitch. Those have vibrational modes that aren't quite harmonic oscillators anymore. There's a sensitivity of the pitch to the amplitude because they're anharmonic oscillators. Anyway, I think I've done justice to musical instruments, and with that, I'll stop.